Let's investigate the matrix representation for the quantum Fourier transform. Over here, we have an n by n matrix. This is the matrix representation for the n-dimensional quantum Fourier transform. This is the quantum mechanical analog of the discrete Fourier transform. We can take all of the information encoded in this matrix and write it in a condensed form. Let's do that over here. So Fn, the n-dimensional quantum Fourier transform, can be written as 1 over the square root of n. This is a normalization coefficient out the front, which you can see over here as well. And then we're going to need two summations. We're going to need two indices. So one index is going to tell us the row, and another index is going to tell us the column. And that information is enough to specify the location of all of the elements in this matrix representation. So let's do that over here. We're going to have the sum of, let's call the first index k, and k is going to go from 0 to n minus 1. And the next index we can call j, and this goes from 0 to n minus 1 as well. So 0 is actually this starting point over here. So we start from 0 and we go up to n minus 1. So in total, we have n entries. That's why this is an n by n matrix. The convention is that we start counting this index from 0. So 1 is actually omega to the power of 0. That explains this row of 1s and this column of 1s over here. Now we're going to have something that actually specifies each of the elements of this matrix. We're going to have omega sub n. So when we see omega in this matrix, this is actually omega sub n. We have to specify which omega we're dealing with. And because this is the n-dimensional quantum Fourier transform, we're dealing with omega sub n. And we're going to raise that to the power of kj. So that's the product of these indices. And then we're going to have a ket-bra combination. The label for this ket is going to be k, and the label for the bra is going to be j. So this is Dirac notation. We have a ket and then a bra. So a ket and a bra, that is an outer product, and we're using this to construct this matrix representation. The order is very important over here. If we have a bra ket, that is something very different. That is an inner product. And we can evaluate an inner product as a complex number. But over here, this object, over here, that is the outer product, and that is giving us an entry that corresponds to each of these elements. So you can see that we have a condensed format that encodes all of the information that is present in this general matrix for the n-dimensional quantum Fourier transform. What is this actually doing to basis states? We can write that over here. If we have a basis state labeled by x, what is going on when we act on this basis state with the quantum Fourier transform? Well, it's going to get mapped to 1 over the square root of n times the sum over the index k going from 0 to n minus 1 of omega n to the power of kx. And then we have the state k over here. So we're taking this computational basis state, and then we're mapping it to a superposition of states. So this k is an index in this summation notation over here, and these omega n's raised to the power of kx, they are the coefficients in this superposition. Another way we can describe this is a linear combination. So we have a linear combination of states, and these are the coefficients in the linear combination. So up here in the product, we have k, which is the index, and we also have x. So that is the x, which is the label for this computational basis state. So this is the mapping that the quantum Fourier transform performs. Now, let's actually define what this omega n is. So it's important that we explicitly define what it means. So omega sub n is a shorthand notation for e to the 2 pi I times n to the minus 1. So this is the reciprocal of n. We can think of this as dividing by n in the exponent. And this is related to the concept of a root of unity. So a root of unity, that is a complex number such that if we raise that complex number to an integer power, we get 1. So that's what we mean by root of unity. And this n over here is can be defined as 2 to the power of little n. So little n is the number of qubits that we're dealing with. These are quantum bits. And big N is the dimension of the Hilbert space. So we can see 3 examples over here. These are 3 example matrices, and they correspond to a single qubit case, a 2 qubit case, and a 3 qubit case. So we're going to investigate these 3 examples because they're very useful when we're constructing quantum circuit diagrams. It's useful to have a matrix representation for that unitary operator that we're representing in a quantum circuit diagram. So let's have a look at the first 2 examples. If we consider omega sub 2, that would correspond to a single qubit, that's 2 to the power of 1. This is equal to minus 1. And if you put 2 over here, you have 1/2. So that 2 cancels with that 1/2, and we're left with e to the pi I. And e to the pi I is equal to minus 1. What about omega 4? This corresponds to a 2 qubit case. So that's if we have 2 up here, that's 2 to the power of 2, which gives us 4. This is equal to I. So you can see that if you substitute 4 over here, you're going to have 2 on 4, which is 1/2. So you're going to have e to the pi on 2 times I. And pi on 2 in this complex exponential, that corresponds to I. So this is very useful. And another important point that we need to stress over here is a convention that is being used. So we have a sign convention. We are putting a plus sign over here in the definition of omega. We could also work with a different convention. We could put a minus sign over here, and then over here we would have minus I. So that is another alternative convention that can also be used. But I'm going to stick to this convention where we have a plus sign over here. And that is the convention that is used to construct all of the expressions in this playlist. So now let's have a look at some of the properties of omega n. If we take omega n and we raise it to the power of k plus n, what is that going to give us? This is equivalent to e to the 2 pi I n to the minus 1. That's just the definition of omega n. And then we're raising it to the power of k plus n. So that comes into the exponent. We're just multiplying. That gives us k plus n. So that is just using exponential laws. We're taking this definition and we're raising it to the power of k plus n. And then we can bring that in as multiplication. And now we can actually break this up into 2 exponentials. So we're going to have e to the 2 pi I n to the minus 1 k. That comes from this term. And then the next term is going to be e to the 2 pi I, and this n to the minus 1, this reciprocal of n, is going to cancel with this n. So we're just going to be left with 1. So that's e to the 2 pi I. E to the 2 pi I is equal to 1. So that means we can ignore this, and we can interpret this as omega n to the power of k. We just have this k appearing over here, and that's the same as raising omega n to the power of k. So what does this tell us? It means if we add n to the exponent, we get back to where we started. It's equivalent. Now, what does this mean in the complex plane? Well, here we have a little drawing of the unit circle in the complex plane. We have a real axis and an imaginary axis. So this imaginary axis is where plus I and minus I lie. And over here we have plus 1 and minus 1 on the real axis. So all real numbers have an imaginary component of 0. And that's why they lie over here. And all purely imaginary numbers, they lie on this imaginary axis. And a general complex number lies somewhere in the plane. But we're restricting ourselves just to the unit circle. So just to complex numbers that live on the unit circle. So this is a really useful visualization. If we consider the physical meaning of n in this geometric representation, what does this actually mean? It means we are slicing up the unit circle into n slices. And if we go n slices around the circle, we come back to where we started. So that is what this means geometrically on the unit circle. Let's consider a related concept of going omega n to the power of k plus n on 2. So instead of adding n, we add half of n. What does that correspond to? Well, if we start to think of this from a geometric intuition, we can actually visualize this as going halfway around the circle. So we've divided up the circle into n slices, and then we are going halfway around the circle. That's n on 2 slices. And what is that going to give us? Well, we'll find out when we actually write this out. So we're going to see that this is e to the 2 pi I, and we have n to the minus 1, and then we have k plus n on 2. So far it's very similar to what we have up here, but the next step is going to be slightly different. We're still going to have e to the 2 pi I, and then n to the minus 1 k, which we can interpret as omega n to the k. So this is still present here. But what about this term over here? Here the reciprocal of n is going to cancel with n, and 1/2 is going to cancel with 2. So we're just going to be left with e to the pi I. So we have e to the pi I. And this is equivalent to minus 1, just like what we found over here when we substituted this value of n up here. We have minus 1 appearing here. So this is going to give us minus omega n to the power of k. So what does this tell us? We have an additive inverse. So if we write this out slightly differently, if we move this to the same side, we're going to have omega n to the power of k plus n on 2 plus omega n to the power of k is equal to 0. 0 is the additive identity. And if we go to this geometric representation, 0 is at the origin over here. That is where the additive identity is. And over here, we're dealing with an additive inverse. So these guys are additive inverses of each other. And they sit at opposing points on the circle. Let's actually substitute some values of n over here. So I'll do that over here. So the first example that we saw was omega 2. So for omega 2, this works as follows. We have k plus 1, and then omega 2 to the k, and this is equal to 0. And then over here we have omega 4 to the k plus 2 plus omega 4 to the k. This is equal to 0. And the final example which we will consider is omega 8 to the power of k plus 4 plus omega 8 to the power of k. This is equal to 0. So these are the examples for a single qubit, 2 qubits, and then 3 qubits over here. So we're adding half of n, and that is giving us the additive inverse. And so if we add this complex number to its additive inverse, we're going to get the additive identity, which is 0. So let's have a look at some examples. So for the 2 qubit case, we're only dealing with plus 1 and minus 1. So if you go to the other side, you have the additive inverse. So if you start off at minus 1 and you go to plus 1, that's the additive inverse. And if you start at plus 1 and you go to minus 1, you also have the additive inverse. Now let's have a look at a slightly more interesting example where we have 4 slices. We're slicing up this circle into 4 parts. We have I over here and minus I. So that's what we're adding to our repertoire of complex numbers. So what happens when we go 2 units around the unit circle? So now we have plus I and minus I. And these will cancel if we add them together. They will give 0. And what about this example? Well, this example tells us that if we go 4 slices around the unit circle, once we've divided it up into 8 chunks, we're going to get the additive inverse. So if we start over here at omega 8, that is going to give us this guy over here. That is the additive inverse. So plus 4 gives us 5. So this is an additive inverse. And if we look at the power of 3 and the power of 7, they're also additive inverses. They will cancel each other out and they will give 0. So we have seen additive inverses, but now let's examine multiplicative inverses. How do we get multiplicative inverses? Well, we take the complex conjugate. And the complex conjugate is the same as swapping the sign on the imaginary component. And that can geometrically be interpreted as reflecting over the real axis. So if we're down here, we go up, and if we're up here, we go down. So this value over here, omega 8, is the multiplicative inverse of omega 8 to the power of 7. And we're actually going to see some very useful patterns emerging in these matrices, and they're related to this concept of multiplicative inverses. Now, let's have a look at these matrix examples for a single qubit, for 2 qubits, and for 3 qubits. The single qubit case is exactly the same as the Hadamard gate. So this is the Hadamard gate for a single qubit. Now, you can see that both 1 and -1 appear in this matrix. So it's a pretty small matrix. It's just a 2 by 2 matrix. And we can interpret the columns of this matrix as where the basis states are getting mapped to. So this 1, 1, this can be interpreted as a superposition of the 0 state and the 1 state. So the basis states, the computational basis states that we deal with when we're describing a single qubit, we can map those ones to a superposition. And this superposition does not have a relative phase, but this superposition has a relative phase of -1. So the 0 state gets mapped to this superposition, and the 1 state gets mapped to a superposition with an additional phase factor. So that is what the Hadamard gate does. And another interpretation of this is we're moving from the Pauli Z eigenbasis to the Pauli X eigenbasis. So this quantum Fourier transform can be used to actually give us a change of basis. We're moving to a different basis. We start with the computational basis, and then we move to the Fourier basis. So this is the first example for a single qubit. Now let's consider the 2 qubit case. Now we're dealing with this sliced up version of the circle, and we're slicing it up into 4 slices. So I and -I, these are additive inverses over here. And they're actually also multiplicative inverses. If we times I by -I, we get 1. And one observation that you can make is that the entries that are occurring over here, we have I, -1, -I, they're the opposite order to the entries in this column. That is not a coincidence. And we're going to see that same pattern occurring in the next matrix. But before we go on to this 3 qubit example, I want you to have a look at this part of the general matrix. So this is the general n by n matrix. If we examine the entries over here, we can actually see that this is exactly the same to this matrix representation. It's just we're dealing with a specific omega. So over here we're dealing with some general omega n, but now over here we're dealing with omega sub 4. That's because it's a 4-dimensional Hilbert space. Now for this 4-dimensional Hilbert space, we're actually operating using modulo 4. So modulo 4, we're dealing with modulo arithmetic. So this is modular arithmetic because we're going around the unit circle. And this is actually an explanation as to why this omega to the power of 9 is equal to omega to the power of 1. So omega to the power of 9, that is 1 more than 8, and 8 is a multiple of 4. So a multiple of 4 is the same as 0 mod 4. So that means we're dealing with just omega. And that's what we see over here. Omega is just I. But what about omega to the power of 3? That's omega cubed. So that's I times another I. That gives us -I. That's what we're dealing with over here. And what about omega to the power of 6? Well, 6 is 2 more than 4. So it's the same as 2 modulo 4. And if we raise I to the power of 2, that's the same as -1. And that explains this -1 that's occurring over here. So that is the use of modular arithmetic. And also if we see 4 over here, 4 is the same as 0. And raising omega to the power of 0, that gives us 1. So that explains this 1 over here. Now let's move on to the 3 qubit case. For the 3 qubit case, we're dealing with omega sub 8. And this is 1 plus I over root 2. So that is this term over here that is living in this unit circle in the complex plane. And you can also write this in polar form, but I'm writing it in Cartesian form over here. And 1 on root 2, that can be interpreted as the value of cosine and sine for this particular angle. And we're dealing with 45 degrees over here. So that is what omega 8 is over here. And so all of these omegas are omega 8. Let's make some observations about patterns that emerge in this matrix representation. So again, we just have our starting point over here, 1s in this column and 1s in this row. That is omega to the power of 0. But let's have a look at some of the more interesting patterns. So we need to identify multiplicative inverses over here. So 1 is its own multiplicative inverse. Minus 1 is also its own multiplicative inverse. And you can see that omega to the 4, that is equal to minus 1. We are dividing it up into 8 slices, and then if we go 4 slices, that takes us to minus 1. And this is its own multiplicative inverse. So what does that also mean? That means it's a real number. Real numbers are their own complex conjugates. And in this context over here on the unit circle, the complex conjugate is the same as the multiplicative inverse. That's because we're restricting this to only complex numbers that live on the unit circle. Let's have a look at 1 over here. This is omega to the power of 1. And let's compare that to omega to the power of 7. So this is omega to the power of 1, and this is omega to the power of 7. They are reflected versions of each other. So they're actually complex conjugates. That means they're multiplicative inverses. And if you examine this pattern that we see over here, we start off with 0, 1, 2, 3, 4, 5, 6, 7. And we look at this pattern, we can also see 1, 2, 3, 4, 5, 6, 7. It's the opposite order. And that is not a coincidence. That is because these are multiplicative inverses of each other. The same pattern can be seen with omega to the 2 and omega to the 6. So omega to the 2, that is up here, that is plus I. And omega to the 6, that is minus I over here. So these are multiplicative inverses, and you can see this pattern of 2, 4, 6, 0, 2, 4, 6. And over here we have 2, 4, 6, 0, 2, 4, 6. And why are we getting to 1 over here? Well, that's because we're dealing with modulo 8. So if we go up in multiples of 2, we're going to have 2, 4, 6, 8, but 8 is the same as 0 modulo 8. So that is why this turns back to 1. And we have this repeating pattern that cycles twice every column over here. Now let's have a look at omega to the 3 and omega to the 5. Those are these elements over here, and you can see that they are complex conjugates. They are reflected over the real axis, and that makes them multiplicative inverses. And the pattern that we see is 3, 6, 1, 4, 7, 2, 5, and that's exactly the same pattern that we see over here, 3, 6, 1, 4, 7, 2, 5. So this happens when we keep adding 3, and this happens when we keep adding 5. So this example over here, if we add 5, that's going to give us 10 over here. We have 2 times 5, which is 10, but 10 is 2 more than 8. So that explains this 2 over here. And this is just the effect of using modular arithmetic. And why does 4, and why does this column over here with omega to the 4, and this column over here with omega to the 0, why do they only have one version? Why is there not a reflected version? Well, that's because they are their own multiplicative inverses. All these other terms can actually be grouped with another term, and they are multiplicative inverses of each other. So that's why we can pair these up. But omega to the 4 can be paired with itself, and omega to the 0 can be paired with itself. And one notable thing that we can notice is that there is a normalization coefficient of 1 over the square root of n appearing in front of all of these matrices. And we can simplify that. We can simplify this to 1/2 if we want to. But we're leaving it out as an explicit demonstration of this general formula over here. So in general, we're going to go up to omega to the n minus 1 in this column, and then we're going to have 2 times n minus 1, and then 3 times n minus 1, and then finally we're going to, in this bottom right corner, we're going to have n minus 1 times n minus 1, which is the same as n minus 1 squared. And we have all these dots over here, and they represent all the intermediate values that are not shown in this general visualization of the matrix representation. So we have seen 3 examples: a single qubit example, a 2-qubit example, and a 3-qubit example. We have observed some very interesting patterns that emerge in the matrix representations of the quantum Fourier transform for a different dimension of the Hilbert space. And we've also looked at some interesting properties of this omega sub n. Why are we interested in the quantum Fourier transform? Well, it's because it forms a very important component of some order finding circuits. So when we create the quantum circuits for order finding and for phase estimation, we're going to be using this quantum Fourier transform. So it's very useful to have a matrix representation in mind so that we can construct matrix representations for states, and then we can act on those states with these matrices. And that is a very useful interpretation of these quantum circuit diagrams. So you can always turn those quantum circuit diagrams into matrix multiplication. And you can verify identities in circuit diagrams by multiplying out matrices. So hopefully that was useful. We're going to be using the quantum Fourier transform in other videos in this playlist.